with Substrates, or like from our learnings with like Ethereum, Bitcoin, and Zcash, and we actually started Polkadot before Substrate, and we realized like a lot of it is the same. So like, yeah, if you think about like what is a blockchain, the thing you really want to focus on is the state. So Ethereum blocks are every 15 seconds or so, and so there's not like a continually changing state. It's like every block is a state transition. That's really like what makes Ethereum, and what makes Bitcoin. Bitcoin is like what is allowed to be stored in the state, like what kind of data structure, and then what kind of changes are allowed. So what kind of functions can you put in this block? What kind of signatures or verification do they need? That's your state transition. The rest of it is like a lot in common. You need like a database, you need telemetry, you need networking, you need RPC calls, APIs. Like 95% of it is the same. The thing that really matters is how do you change state. And so kind of in the beginning, that was like, there's going to be like Bitcoin, Ethereum, just a couple chains. But as that's changed and we thought, well, we have to build like a lot of blockchains, it's kind of crazy to be repeating the same thing over and over again when really only 5% of it is different. So the whole point of Substrate is that it takes care of everything and you just get to focus on this state transition part. So yeah, a lot of this came out of like a belief that there will be a lot more application-specific chains instead of just smart contracts on a single platform. So a few reasons, like you get to optimize your state machine. You don't have to worry about what anybody else would want to do. You get to define your RPCs and APIs. So the attack surface is small. You get to just say this is what you're allowed to do from the outside. You don't have like the EVM is very low level, and so like these languages like Solidity that compile from a higher level down to a lower level. Some people miss a lot of abstractions, which is what leads to bugs. So if you can have just a smaller attack surface, that's better. You get to decide what to do with it, so you don't have to worry about what other people will do, and you're not bound with the platform limitations. So like if CryptoKitties becomes super popular and then it's more expensive to do transactions on your chain, but you have like nothing to do with CryptoKitties, that's obviously a disadvantage. But the con of that is like, the network effects, like if you do want to have something to do with CryptoKitties, like it's actually nice to be in the same network. And then it's hard to build a chain from scratch, which we hope to fix with this, and the network effects one we hope to fix with Polkadot. But there's still some like benefits to smart contracts, and we do have some smart contract chains in development on Substrate. Like the main one is the resource control. So like Jack said, like Polkadot has no concept of gas, and neither does Substrate really in the runtime. So anything you design, you have to kind of think about like what is the cost for this. So if you want to implement some really complex logic, that's fine. But if you're letting your users call this complex logic, then you need to have some way of punishing them so that they don't abuse it. So like with gas, it's pretty simple. Like you just meter it. But some things like, it turns out voting is actually like quite intensive because everybody's like putting their votes into a vector, and then you have to like iterate through this vector and to tally the votes for each referendum. So if you want to vote, you have to stake some money or lock it that is slashable. So yeah, you have to kind of keep that in mind when you develop your runtime, which is our word for the state transition function. So yeah, this is like an overview of our architecture. So libp2p is networking, and then consensus and the core stuff, and then the runtime sits inside of WebAssembly. Everything's written in Rust, and the cool thing about this is that WebAssembly is the virtual environment, in case anyone doesn't know. But like the WebAssembly interpreter is part of the core, and so you actually take your runtime and compile it into just a binary that goes actually in the chain. And when a node executes a block, it's going to check like what's the version of my client versus what's the version of the binary in the chain. And if they're the same, it'll just execute the native client because it's just going to be faster than running an interpreter. But if the binary on chain is a higher version number, then it's going to run that, and that lets you do on-chain upgrades. So like with Ethereum or Bitcoin, like if you want to upgrade the system, you have to get every single node to upgrade. Otherwise the network forks. This allows you to upgrade the chain in some way through governance, put a new binary on the chain, and then people can upgrade in time to get the faster performance. But the chain doesn't fork because you'll just kind of go into running this WebAssembly or running your chain in the WebAssembly environment. So we break Substrate into 3 levels: the core, the runtime module library, and then the node. Not going to talk much about the node because it's actually like just a composition of the SRML that's like the default out of the box one, so that you can like just download it from GitHub and start a blockchain running. But most people are going to be working with the SRML. So pretty quick on the core. Like, yeah, this is the low-level stuff. So like the databases, the crypto libraries, telemetry. The consensus is cool. So we have it pluggable right now. So we have like a few different consensus algorithms, and you decide at the beginning which one you want to use. We would like to make it swappable so that you could actually upgrade your runtime and just switch to a new consensus algorithm. But we're not quite there yet. So yeah, we don't really envision people changing this. So like for crypto, we use like SR25519. Ethereum uses like SecP256. So it would be like, if you want to make like an Ethereum 1.x client with Substrate, then you have to go and like change out the crypto library, which will affect like everything above it that validates signatures, which is basically everything. So unless you're like trying to build to match a spec, then you probably don't need to touch this. But if you're speccing a change from scratch, and there's like, if you're happy with the hash function, if you're happy with the crypto library, like unless you have a really compelling reason to change it, then you should generally be okay with the core. Otherwise, you'll have to make a lot of changes up higher in the stack. Yeah, SRML, this is like kind of the real interesting part. So we provide all of these modules. You can modify them or write your own to add into them. But these were basically just like a bunch of interfaces. We're trying to abstract it out so they're not so like quite so dependent on each other. But they just provide like trait implementations, and you can just decide to include these trait implementations or calls into your runtime, and they're just available for you. So like if we have a democracy module, like if you want to have public voting on things, then you can just implement this and you have all the functions that you need to hold elections and tally votes and enact the actual decision of the vote. Yeah, and it includes some like JavaScript and front-end interface stuff, all the block authoring, transaction queue logic, and Emil will like the Chain Explorer. Yeah, so these are some of our modules. You can go into like detail on some of them if you want. Maybe I'll go a little bit farther and come back to this one. Yeah, and so like what happens when you actually compile your runtime into a node is it's just basically like we have these macros that build all these things. So like calls, these are your dispatchable functions. So this is like what people at the front end can call, like your users can call this. And these basically like, so like each one of these will have some of these dispatchable functions. They get put into an enum, and then we have like a master enum. So there's like a, like a balances enum with all of those calls, and then there's like a runtime enum with the balances and then the assets and all that. Origin information about like where the call came from. So yeah, like if an outside user calls something, then it's like automatically has like the origin as like their account. And then it comes with like some privilege too. So you can designate certain accounts as having like more privilege than others. And then storage. So there's like a way to declare what kind of things you want to keep in storage in your runtime. Events. This is like how you just tell the outside world, hey, something happened. And then inherents, just kind of like an oracle. So in Substrate, we don't specify, like our header isn't that large. It's only like it's like 5 things. It's like a pointer to the last block number. It has the storage root, the block digest, and I'm spacing. I can't think of the last item. But like most other chains have a lot of stuff in their block header. So like they'll have like validator set, the nonce if it's proof of work, timestamp, all this other stuff. Like we don't put that in the header at all. That all goes in the block. So like you don't even have to include timestamps if you don't want to. And so like what separates inheritance from normal transactions is like they're not really true the way that like a transaction is true. So like you can prove like, yeah, I wanted to send money to somebody else because I signed this message. The inheritance are stuff that generally speaking only the block author can put in. So this is like the time. Like there's no way to say like, it's 1932 because different clocks are different. That can't really be true the way that I want to send money to somebody else is true. But you can really put like anything in there. So like one of the guys at work wrote a module that just like goes to the CoinDesk API, fetches the price of Bitcoin, and just puts the price of Bitcoin in as an inherent. So it's really only validated as long as people agree that it's true, because if somebody else goes and tries to validate that and calls it API 2 seconds later, they might get, or probably will get like a different result, but you can define the rules for validating these things in your runtime. So you can say as long as it's within 2% of what was submitted, then we're just going to say like that's true and we'll write it into the block. Yeah, and then you get the node, which is like just kind of a generic blockchain, but basically all of this stuff gets compiled into the node. So yeah, I think that was it. Oh, and then Polkadot versus Substrate. So like Polkadot is like a protocol. So you don't have to build parachains with Substrate. It's the easiest way to, but Polkadot is just a protocol. So it says that, if you want to be a parachain, you need to submit this type of information to the validators, and you need to provide this interface. Substrate would be more like React as a framework, so it's all the tools to build a blockchain, but it's not a protocol. And then here we can go into some of these modules. If you want anything in particular, like Grandpa, okay. Yeah, so Grandpa is our finality gadget. What we did here is we actually separate finality from block production. So in proof of work, these are like kind of integrated. But in proof of stake, you can how do you decide who can even author a block? That's kind of a big thing. So we have 2 block production algorithms right now, Aura, and another one that's not on here is called Babe. And Grandpa is a way of finalizing these. So these block production algorithms will just, they're kind of probabilistically final. They will just keep submitting blocks off of the longest chain that they have, which may not correspond to the highest chain that's been finalized. So the blocks that are being produced could actually be 10 or 20 blocks ahead of what's been finalized. And so where Grandpa comes in is it's similar to Ouroboros Praus, which so most other finalization mechanisms and proof of stake chains are finalizing a block. So in Tendermint, you submit a block for finality. It gets a pre-commit vote, and then once it passes that with 2/3, it goes another vote, needs another 2/3 to be finalized, and that's going block by block. Grandpa goes by a chain, so the nodes are actually submitting the block header of the longest, or not the longest, but the chain that they consider to be the best chain. And what it does is it can derive from the block header of the longest chain from one validator the ancestor blocks in that, and it'll just keep taking back the ancestor of these parallel, or these chains of these parallel chains, and it'll find where they have a common ancestor that has more than 2/3 that are agreeing that is the final chain, and so that becomes the latest finalized block, and then everything below it gets finalized along with it. So if you have, most proof of stake, it's liveness versus safety trade-off. A PBFT chain would be safe. If it doesn't finalize a block, it'll just stop producing blocks because it's waiting for this block to get finalized. By separating these two, we'll keep producing blocks, and then we can just finalize like a whole chain. So if you have a network partition, these chains can keep producing blocks, but they might not have like enough of the whole validator set to finalize anything. But then when they come together, they can find what they agree on, and they could finalize like 1,000 blocks just in one shot. Yeah. Any others?
These are example modules that Parity has developed.
Yeah.
And Web3 Foundation has researched mostly. And the thing is that with Substrate, any implementer of Substrate, user of Substrate, can implement their own modules, right?
Yeah, so you can write your own module. Similar thing, it just needs to provide certain interface, like basically a macro that creates an enum and another macro that creates a struct that the runtime or the node can compile and just basically import it into the runtime. So yeah, you just need to provide an interface with these modules, and then in your runtime you can include them and do what you want with the functions and just make your own logic with them. Yeah, Web3 has done a lot of research on like the staking and the council modules especially.
So for others, they could actually use these modules. It doesn't make much sense unless you have very particular needs to rewrite a balances module. If you need a token in your runtime, then
No,
you would use
like
the balances module, right?
yeah, we have balance. Yeah, exactly. That just supports like your Ethereum style key value database of accounts and balances. It's not listed on here, but somebody wrote a runtime that does UTXO set accounting also. So you don't have to use accounts and balances. But this also provides like a multi-currency implementation. So balances provides a few traits like currency, lockable currency, reservable currency, and investing. Just different features along with these currencies. But yeah, you can even instantiate multiple instances of these. So if you want to have a 2 or 3 currency system, you can just use the balances module 3 times and define 3 different tokens.
Joel, in the beginning,
Yeah.
you mentioned that Polkadot was there earlier than Ethereum. What was that?
Earlier than Substrate.
Oh, I see. Can you elaborate on that a little bit?
Yeah, I mean, I wasn't at Parity at that time, so I can tell you what I've been told. But yeah, people started working on Polkadot, realized that a lot of this work was kind of the same thing they had done before with Ethereum and Bitcoin. And then I think they actually forked that off and like made that Substrate, and then like kind of took Polkadot as the separate branch. But I don't know exactly. It was but it came out of developing Polkadot of like, why are we doing the same thing again? Just put it into modules that we can compose, which is generally good software engineering practice anyway. I did most of the documentation on these, so if you want to know, you can test me. So. Any other questions?
What is pseudo?
Yeah, so in your calls, you can define this thing origin, and it basically tells you like who the sender of this, kind of obvious, but who the origin of this call is. If you don't include it, it will automatically assume that the origin must be root. And so there are 3 different origins. One is root, one is the user, and one is the council. And so, yeah, the pseudo can basically call any of these functions. They're usually lower level functions. Only one account can be pseudo. So yeah, a normal account would be like a just user in Linux, and pseudo, the person who has this pseudo key would be like the root user. So this provides really low level functions like changing somebody's account balance. Yeah, that would be like kind of recovery type situations, not to be used really often. And yeah, to be used with care, but it can only be one account. It can change, but it can only be one at a time.
Could be handy for proof of authority type chains as well.
Yeah. Yeah, like a pseudo could, if you want proof of authority, you could have pseudo who kind of decides who the authorities are.
If you trust a consortium to take care of stuff,
Yeah.
you could give special rights to.
Any others? Yeah. Yeah, Aura. So Aura is our current one. It will be replaced by Babe. Well, Aura will be available. You can use whichever one that you want. Yeah, so Aura is kind of just like, so in like proof of stake algorithms, you need a way to determine like who's allowed to write the block and submit it to the network right now. And so Aura just basically like breaks up into time slots. So it's usually like 5 to 10 seconds, and it says like, okay, for 5 seconds, like this account has the right to write and propose a block to the network. And if it doesn't in this time slot, then it's just going to move to the next slot and give the authority to the next person. And Aura is just like round robin. So you have your validator set, and it just goes around in a circle, and they're taking turns. It's not great because you can see it's kind of susceptible to a DOS attack. Like if you know who the next validator is, you can just DOS him. And like if you're one of the validators, you can just keep DOSing around in a circle until it's your turn. Yeah, so what we're doing on that is Babe, which I can't remember what it stands for. But it's using like a VRF. So you have like a secret key that goes along with your account and like your permission to be a validator. And then these slots are actually like on the order of milliseconds instead of seconds. And you're basically like always checking based on this VRF. It's almost like proof of work if the output of this VRF is below some threshold. And so we define a threshold, and you just keep checking, like you just keep running this random function with your secret key. And when you get an outcome that is below this threshold, you have permission to write a block for like the next 100 or 200 milliseconds. And then you can just submit a proof to the network that, yeah, my VRF at this time, I had the permission to write the block. But actually at most of the times, nobody would have permission to write a block, right? So you kind of expect like that whatever your block time is, like if you want a 5-second block time, then you'd expect that like every 5 seconds, somebody will get permission to author one of these slots, but actually most of the slots don't have a valid block author. Just people are continually checking to see, do I have permission, do I have permission? And you can even end up in that case where 2 or 3 different validators have permission because they just, by sheer randomness, we're all below this threshold, which is where grandpa comes in and decides like which one of these things will be final. So that's good. In the back, you had a question? Yeah. Cool. Thanks. Good.